My name is Glinko. I'm working as a machine learning researcher at DAC.digital, the company which next to the deep tech is also working on software and embedding systems. And I will tell you something about meta-learning, so a little bit different approach than standard gradient backpropagation training, but very beneficial in some cases. First, I will present you some necessary to understand the topic meta-learning definitions, like what is the meta-learner, what is the inner learner, what is the task, what are the tasks. Then I will present you a few examples of a few-shot learning architectures, which are architectures to perform meta-learning for image classification. And then I will present you a demo on anonymized data from our company. I can tell you the detailed use case and hyperparameters, etc., because we are working on the academic paper on this topic, so very sorry, but I think the example will be enough. Okay, so let's start with the meta-learning definition. The meta-learning basically is learning how to learn. So we are trying to utilize the previous knowledge which we acquired in the past. We are not learning from scratch, but we are learning from some point. And the most popular paper about the meta-learning says that learning quick is a hallmark of human intelligence. So people are able to learn new tasks by just a few repetitions or just a few minutes of manipulations, and you're able to perform a new task. This is not the case of standard backpropagation training of neural networks, where you require tons of data to train your model to perform well. But first, to catch your attention, let me give you a task. It's from the cognitive psychology paper, and it shows very well what is the human approach to learning. So please find all tufas. Tufas is the word from the alien language, and example tufas are marked with the red squares. Yes, and your task is to find all tufas among these objects. I hope you will perform very well on this task, but you have only 3 examples to learn. Like, imagine you're a neural network and you have to learn object classification. I give you 4 training data points, and now you have to classify all the rest data points based on this input. Okay, I think you all completed the tasks, so the answers are marked in the gray boxes. I hope you get 100% accuracy, but if not, no worries. Like, models are making mistakes too. You had only 3 data points, but you now know that training data classifier with the image input is not possible with 3 samples. The network will be highly overfitted or underfitted, depending on the scenario, but probably very overfitted if we train over a lot of epochs. And yeah, so having this knowledge and basics of meta-learning, I will tell you where it's beneficial to apply meta-learning approach. For example, when the annotations are very expensive, like in the medicine. In the past, I was working in the competition where our task was to classify the stroke etiology based on the biopsy images. And what I found in the medical papers, biopsy images of stroke etiology are labeled in the way that 3 doctors have to annotate the data, and the data point is considered as a valid only if 3 doctors agree. All 3 doctors has to agree on the data point, and only 60% of data are accepted and 40 are rejected. So this is very expensive. This is a very expensive process of annotations. You have 3 experts, and 40% of data points are thrown away to the trash. Yes. So, but you have previous data sets where these biopsy images are annotated, and basically the input is the same, but you want to look for a little bit different things. So you can apply this meta-learning when you learn your model to adapt well on with just a few examples of data, or when you have a small amount of data. For example, if you are trying to classify new animal species, there is very hard to make photos to annotate, but you want to classify them. You have expensive training. For example, you have an industry process when you try to classify or segmentate some screws, valves, etc. And these details are changing very frequently. And using meta-learning approach, you don't need to retrain the whole network for the big on the big data set, but all you have to annotate few examples, train the network, and your network is easily adjusted for a new task. So you save money for training, like ChatGPT, for example, few millions of training, a few $1 million training costs AWS. So expensive training is really a problem if you have big models. Okay, and if calibration is required, and very good example is speech recognition, when you have to say, "Hi Alexa," "Hi Google," or something like this. So you are giving your network some fine-tuning examples, and the network is trained on these few speech data points. And like classic neural network fine-tuned on few data points will probably overfit. But if you use meta-learning approach, you can train your network to get the better results than the network without calibration. So this is called domain generalization. If you train a model on the speech of some population, and then you want to adjust this model to speech of the given subject. Okay, so let's move to examples of few-shot learning architectures, which are architectures performing classification of images, but in this meta-learning scenario. And the most important is the task definition. So we move from the standard data set with thousands of labeled data mixed together to a little bit smaller batches called tasks. And every task has data points, annotations, and a loss function. Loss function is very important because it's the thing connected with the task. For example, if you want to classify images, your loss function connected with your task is categorical cross entropy. And if you look carefully at images, it's not a mistake that in the first task the plane is class 1, and in the second task, these are examples of task, plane is class 2. We want to train model to be task agnostic. So task is like a separate job. It's like your whole data set, and your goal is to train a network that which on the basis of previous knowledge learned from the tasks, and is to perform well on the new task, new unseen task. So these classes are unseen, or they can have mixed labels, like plane class 1 in training, but in validation class 2, or car class 2 and in validation class 1. And we have a meta-training and process, and then we have a meta-validation process. So in the meta-training process, in the support set, classes are known, same as in the query set, but during the validation set, only support set labels are known, and our task is to predict query set labels. So to sum up in few words, we are minimizing the validation loss. So, but it's the not real validation, because real validation is the meta test query set. So it's quite counterintuitive that while the testing stage we have some annotations, but these annotations are different job, right? It's like training whole network for different job, and the task doesn't need to have the same job to do. For example, first task can perform image classification, while the second task can perform, for example, segmentation. If we can share some knowledge, like feature extracting of the image, we can share the knowledge among the network, so it's called multitask prediction. And the definition you can find in the meta-learning architecture is like something is n-way m-shot. So n-way means number of classes in the task, and the m means number of data points per class in the support set. So we train on the m data points and of each class, so we have m times n data points for training, and then we validate on the query set. And the query set can be of any size. Just to sum up, so for the meta training, you have a support set ground truth both and query set ground truth, but in the validation, so-called meta test, you have only support set ground truth, and your job is to predict the query set labels. Okay, let's move to the real examples of architectures. And first, the very simple one is the transfer learning. But transfer learning in this meta terminology is not a standard transfer learning when we take the networks, take the weight of the pre-trained network, and we just apply our data and okay, we want our network to generalize well, but this is a small trick that we train in the training phase. We forget in this architecture for a while about task. We mix all data set together and train feature extractor, and classifier is only to compute loss function, right? Because you have to apply gradient back propagation, so you have to compute a loss to compute a gradient. Okay, and this is the meta training phase, but in the meta test phase, for each task, you delete your pre-trained classifier, and you only the fixed feature extractor stays on its place. And for each task, you build a new classifier, and you try to fine-tune this classifier only with this just few support set samples. But these architectures are quite good, but they suffer when there is a big domain gap. For example, your training tasks are planes or something flying in the air, and in your meta testing stage you have something like boats or underwater stuff. But in the other cases they work very nice, especially for deeper backbones. Okay, let's move to the second group of few-shot learning architectures. This group is called metric learning. So we are trying to learn how to compare. And first, very simple approach is our Siamese networks. So we are embedding our images in the latent space, and then we compute some scores like Euclidean distance of features or cosine similarity. So in the meta test set, in the meta training stage, you just extract features and train your network, extract features, and you compare every query set with every support set. So this is quite exhaustive comparison, but this is very first architectures, and they are not much competitive now. And now in the meta test, you just apply the same procedure, but in the meta training stage, you compute meta loss on the basis of the query set, and then you backpropagate your loss to update network weights. And very second architecture in the group of metric learning is very interesting. These are prototypical networks. Nowadays they're extended for the segmentation, not only classification, but segmentation. Meta segmentation is out of the scope of this presentation. We don't have so much time. And these networks, prototypical networks, simulates k-nearest neighbors, but features are extracted by a feature extractor. So in the support set, we are extracting features and we are making prototypes. So prototypes are just averages of extracted features for each class from the support set, and these are prototypes. and then we do the same with the query point. And we compute the distance from the prototypes, and the nearest distance, the closest prototypes, is just the predicted class, and we backpropagate the meta loss calculated on the query set. And in the meta validation, meta testing, we're just doing this comparison. Extension of Siamese networks are relation networks. So instead of computing a single distance or metric, something like, so we remove handcrafted features in favor of additional neural network. But the beginning of the process is very similar. We are computing latent space, so we are computing embeddings of the query sets, of the query set images. Then we concatenate these feature maps with the feature map of the query data point extracted by the same feature extractor, and then each of these stack is processed by the second network, and relation score is computed, and then softmax or another function is applied to compute probabilities, to compute loss, and to backpropagate the meta. In the meta training, we backpropagate the query set error. So let's move to the third group, and to the model-agnostic meta-learnings, and I will show you how we in DAC.digital applied the model-agnostic meta-learning for solving multitask regression problem with calibration. So we have a model trained on the group of data, and just we have in the process we have some calibration points, and we want to utilize these calibration points to train our network, but we don't want our network to overfit or something. Okay, so model-agnostic meta-learning, I will present this algorithm in a little more details, but the case of this algorithm is not to learn weights of network that generalizes well, but we want to train network that with a few gradient steps can be easily adapted for a new task. Okay, so we have two optimizers, inner optimizer and meta optimizer, and starting the process, we initialize parameters of our networks, and for the support set, we make a copy of our weights, and we apply standard gradient backpropagation training on the copy. So we are making few steps, and the number of steps is a hyperparameter of the algorithm, and we are making a few steps to move toward the best solution for the given task. And for the last step, we are now computing loss on the query set, and this is our meta loss. And then we pass this meta loss to compute the meta gradient, and the gradient, this is the drawback of this algorithm, has to be computed through all these steps. So each step is a network through which the gradient has to be computed. And the last trick is that the weight update is made not on the step, but on this first initialized parameters. Like, so we make a copy, we train the copy, then we validate, then we compute loss on the query set, and then we go back to the original network, and on the basis of this gradient from the last inner step, we compute our update for the meta learner, right? So we have this. So we have inner learner trained on the support set, and we have meta learner trained on the query set. And the model agnostic means that this approach can be applied to every type of network. So from regression to classification, segmentation, even reinforcement learning can be trained in the model-agnostic meta-learning approach. This is very popular paper in the meta-learning topic, the most popular, and I will show you the benefits of training the neural network with the model-agnostic meta-learning approach. Okay, I told you about some drawbacks. So we have to propagate the gradients through all this copied network. So for example, if we have two inner steps of our inner optimization, we have to backpropagate gradients through two copies and one original network to update weights. So the problem of vanishing gradients occurring very often, and but there are solutions in the literature, and this is the multi-step loss optimization. So we don't compute the loss from the last step, but we compute loss from every step, and then we are doing the weighted sum of these losses. And when the training is processed, the weights are changing in favor of the last step to end up with the weight of the last step 1 and first step 0. And unstable training can appear. This is due to the constant meta-learning learning ratio parameter. Some tasks are easier to learn, while some tasks are harder. So training the network with the constant learning ratio can lead to unstable training. But if you apply simple cosine annealing of meta-learning ratio, you can stabilize your training very well. If you want to dig deeper, you can read the paper about implicit gradient meta-learning, which will allow you to train your network for infinite number of steps, because we are in the implicit gradient meta-learning. We are training the network, and we are assuming that we are trained to the local minima, so the gradient is 0, and with Hessian and the second derivatives and some matrix inverse, we can compute the update without propagating the gradient through all networks. Okay, and for fair comparison, I will present you a setup of the experiment. So we have a ResNet backbone with two task-specific multi-layer predictors. So this is a multitask prediction, and we have the same architecture. So the same architecture is trained in the standard backpropagation method and in the model-agnostic meta-learning with these improvements presented before. We have same learning ratios, so standard learning ratio is same, inner learning ratio is same, and the meta-learning ratio is same. We have the same iterations number, so iteration is update of the standard neural network with one batch. And in the case of the meta-learning, it's just learning on one task. And the batch size in the legacy training, same as in the model-agnostic meta-learning query size. And in the meta test, input batch is same as test query size. So this is very fair comparison. We make everything to don't make it in favor of model-agnostic meta-learning. We want to show a real comparison. And on these charts, you can see the data is anonymized, so we call it just task 1 and task 2. I won't tell about the metric of the error, but the overall, you can see that on the left chart, we have a number of support set size, so the number of calibration points applied for the network with the constant gradient step size. And you can see that green one and the red one, so the predictions of the standard network for this task after calibrations required stays the same. But model trained in the model-agnostic meta-learning approach can be fine-tuned very easily, and you can see that for the first task, even 2 calibration samples can give us superior performance, while on the task 2 we need a little bit more calibration data points, but for 10 you can see that the performance is better than the standard network. So if you have 10 calibration points, you can train your model with the model-agnostic meta-learning way. And on the right side, you can see how the validation error changes while we apply the various number of gradient steps. So gradient steps is just a single update. We make a forward pass, we compute loss, and we make standard back propagation, right? So in the fine-tuning, in the model-agnostic meta-learning, we have standard back propagation training, so only the inner training, no meta training anymore. And you can see that increasing number of gradient steps with the constant number of calibration data points gives you a better performance. So just for 2 gradient steps, you have the same performance on task 1, and when applying 2 gradient steps, you have a better performance or on task 2. Okay, but let's apply some more aggressive fine-tuning. So now we have 50 data points, and we are doing 20 gradient steps instead of 5, and we make a learning ratio like 20 times higher. So we want to fine-tune our network very aggressively, and we want to observe what happens. And you have a chart of error on task 2. And on the left side, you have a model-agnostic meta-learning results. So model-agnostic meta-learning without fine-tuning is just 0 calibration steps. So this is like more than 1.3, and this is the same. But after fine-tuning with this aggressive policy, you have a very big improvement. But this improvement is not scaling to the infinity. It has some plateau, and we find this plateau near this scenario. So adding the gradient steps or increasing learning ratio will not scale to infinity in terms of better performance. But on the previous slide, we observed like no reaction of standard neural network on fine-tuning, but during the aggressive fine-tuning, you can observe overfitting. So the data points there are too low data points to effectively train standard backpropagation neural network. But when your network is trained in the model-agnostic meta-learning, you can apply this fine-tuning quite effectively. In the term of task 2, there is no big difference in the performance of untrained network, untrained like no fine-tuned model-agnostic meta-learning network. But in the task 1, you can see there's a quite difference in favor of standard network. But this is our trade-off. So we don't want to, one more time, we don't want to train network that generalizes well, but we want to train network which is easily adaptable with just a few gradient steps. So we agree on a little bit worse performance when no fine-tuning is applied for model-agnostic meta-learning network. So just to sum up, I show that a good initialization just a few gradient steps away from a solution. So this is what these previous charts are saying. So fine-tuning model-agnostic meta-learning is very beneficial because the weights are easily adaptable. And the last charts, meta-learning can prevent neural network from overfitting when there is very few data points for the fine-tuning stage. So if you are applying a soft fine-tuning, there's no improvement or no or no overfitting, but if you're applying very aggressive fine-tuning, you can observe overfitting, which is what we expect, like with a few data points. And meta-learning can help to solve that data-restricted problems, like long-tail distribution problem when some classes don't have much data points to be trained off. So you can apply meta-learning, metric learning to classify, or model-agnostic meta-learning if you want to perform other tasks with your network. Okay, that's all for me. If you have any questions, feel free to ask.